Okay, following up on a recent video where we did the Fourier series of e to the x, today I want to do something just a little bit different, do same function, e to the x, same interval, but now we're doing the complex Fourier series. I think this is going to go quite a bit quicker because in this case we just have one constant. These formulas are also easier to derive, so I think my finding is that generally like this always goes faster. Well, not always, but just in my experience it usually is faster using the complex Fourier series. So to get started with it, we'll just go to our definition where we'll take our L from our interval. What we're going to want for this is we're going to want L equal to pi. Let's find this C sub n constant. So what's going to happen, plugging in for the 1 over 2L, that's just going to be 1 over 2 pi. Then we're going to be finding an integral, which is going to be going from minus pi to pi. F of x, plug in our function. Another reason why this is going to work so nice is because we've got the same base, so that's going to help us out too. When we do this, with L being pi, basically that's going to cancel right there, and so this is going to become e to the minus nx dx. So then I can rewrite this when we multiply this together. What's going to happen is then multiplying these together with the same base, add the exponents, I'll factor out an x, so I can write it as e to the 1 minus in times x dx. Go ahead and integrate. What's going to happen? First, we just get back the whole thing, e1 in x. Then this is just going to pop out in the denominator, 1 minus in from minus pi to pi. Plugging in, I think I'm going to start rearranging it. So with this, we can look at it, breaking this up. I think I want to do it like e to the x. I probably should have just done this before, but now let's put it in this form. So we want e to the x over e minus nx. So then when we plug in, we've got a bunch of constant stuff out front. So I'll write it 2 pi, 1 minus in. We plug a pi into this, we're going to have e pi over e minus in pi. Minus, we plug in minus pi, we get e minus pi. And this is just going to become the same thing with a plus sign. But this is pretty nice because when I get a common denominator, if I multiply e in pi here and e minus in pi here, what's going to happen? You get e to the 0. So what happens is this just becomes 1. Of course, I need to do it in the numerator. So we're going to have e in pi here, e minus in pi here. But let's just look what happens for this term when we put this back into Euler's formula. And also, we've got the positive and the negative, so let's do it like if this is plus or minus n pi, and you put this back into Euler's formula, you got cosine plus or minus n pi plus I sine plus or minus n pi. But here, integer multiples of pi, sine's always 0, so this part goes away. Cosine's an even function, so cosine doesn't care about plus or minus, that goes away. And then what happens here, the odd terms are all going to be minus 1 at like pi, 3 pi, 5 pi. The even terms are just 1. So I can take this thing and write it as minus 1 to the n. So let's put all this together and see what we have for our constant. It's going to be minus 1 to the n. All that we're left with here is e pi minus e minus pi over 2 pi 1 minus in. And so this is going to be our C sub n value. Let's take this, plug it back in, and see if we can finish this thing off. Okay, so what I've done now is we've taken the constant that we found on the previous board, plugged it into our formula for f of x, which is our e to the x. So we're saying e to the x now. So we're saying e to the x is going to be this sum, where we've plugged in all this stuff over here is just our C sub n value. Over here, the L value is pi, so that's going to cancel out. That's how we get this e to the inx here. Now from here, maybe technically you could leave it, but let's try to get it to look like what we had from the previous video where we didn't have, we had it all real for one thing. And also we have some constants inside the sum here. So I can factor that stuff out front, so we can have this as e to the pi minus e minus pi over 2 pi. And then for this sum, I want to start breaking it up. So let's break it up into 3 pieces. For the first one, let's go from minus infinity to minus 1. Because again, we're going from minus infinity to infinity. I want to capture all the terms. So let's do another sum from 1 to infinity of really all the same thing. And then the only thing we're missing from this is the n equals 0 term. Well, we can just get that and plug in. So if we plug in a 0 for the n values everywhere, here we get a 1 here, a 1 here, and a 1 here. So we have 1 over 1, or we're just going to have a 1 over here. And then next, all I want to do is fix this one and get rid of all these negative terms. You could do like a substitution, like something like n equals minus k to flip the sign around. Let's just kind of do it on the fly though, because when we can change the variable back, we're just flipping the sign on everything. So we can do this without changing anything. We just need to change our sum now. We need to make this go from 1 to infinity. And then we're going to have a minus on this one. Minus here is going to turn this to a plus. Putting a minus there doesn't do anything because it's still going to be the same thing as minus 1 to the n. So we'll just leave that one the way it is. And then what that's going to allow me to do is pull these two sums together. But let's just simplify the fraction before we do it so I'll save myself some writing. So what's going to happen if we pull these together, I can factor minus 1 to the n out front. So then we're going to have e minus inx over 1 plus in. And the other one's going to be all this stuff. But then from here, let's get a common denominator, multiply in 1 minus in here and 1 plus in here. But when you multiply this out, what's going to happen, like difference of two squares, for this denominator, it's going to become 1 minus I squared n squared, but I squared is negative 1, so this really becomes 1 plus n squared. So let me rewrite it, and what's going to happen, we'll have the first part. I'm going to reorder things. Let me multiply in 1/2, taking the 2 off the pi and reordering it. Half times 1, this is going to be 1/2 here. Then I'm going to have 1/2 in front of this sum, which is now just going from n equals 1 to infinity. And let me clean up all this stuff and see what we have. Okay, now from here we're getting somewhere, but we need a little more simplification of all this. When you distribute this out, I'm going to do this part kind of quick. What we can do, let's just focus on multiplying it times the 1s. If we just focus on multiplying that in there, what we're going to have, we can write this as einx plus e minus inx distributed in the 1/2. And then what we have right here, this is actually the complex definition for cosine nx. And then we can do the same kind of thing with these in terms. What that's going to be, let's see, if we put that all together, we're going to have, let's like factor, I could factor it like this, right? In in front, einx minus e minus inx. Same thing, bringing in the 2 here. If I multiply by I over I, this becomes a minus 1. Well, then what is this thing? It's going to become just minus n sine of nx. So all I need to do is take this, and sorry for the mess, but plug it back into the denominator and let's see what we have. And then what we have here, this is going to be our Fourier series definition for e to the x. This is the same thing we found in the previous video with a little bit of work getting it out of the complex form. Now before we finish it off, let's just get one nice value from this. Let me clean up the board and we'll see if we can do something with this. Okay, so now that we've got this definition for e to the x, let's try some things. So what I want to do is I want to plug in e to the pi here and see what happens. The first part, this is just a constant, so that's not changing. Now plugging into cosine nx, what's going to happen is now we have cosine n pi, and then for the next part, this is just going to become sine of n pi. But again, with n being an integer, sine n pi, that's what we found before. That's just 0. That's going to all go away. This right here, this is the same thing we did before as well. This will be found to be minus 1 to the n. But when you multiply minus 1 to the n times minus 1 to the n, you're going to have minus 1 to the 2n or minus 1 squared to the n, however you want to do it, but that's just going to be 1 to the n or just 1. So it turns out the whole numerator just becomes a 1. I can get rid of all this. And then what we've done is we've created this series that I did a week or so back, and we can manipulate it like we did in the other video and solve for this, and we can get a value for this sum. Now there is a couple complications. One thing is the convergence on this is it doesn't include the endpoints. And I on purpose chose an endpoint where it doesn't converge, so that's a problem. Another thing you'll notice is let's plug in the other endpoint. Let's look what happens for e minus pi. Well, what happened when we plugged it in? I got the exact same thing, just more compact because I didn't have to clean it up, but this is the same thing as this. just because the same thing happens, the sine term becomes a 0, this becomes minus 1 to the n, you get the same thing. Now here's where there's obviously a problem. If you just plug this into a calculator, this is something, it's kind of close to like 3 to the 3, but it's actually more like somewhere around 23 point something. If you do the same thing with this, like 1 over e to the pi, it's like, actually it's just the reciprocal, right? 1 over 23, it's something like, I can't remember, something like 0.04 maybe? So how is it possible that we have the exact same expression for 0.04 and 23? It's like it's saying that these two things are equal when they're clearly not even close to equal. Furthermore, if you calculated this sum with some other method, right, and plug everything back in, then everything is just a constant, and you calculate this sum, this whole right side, it's something, I don't know, it's like around 11.6. So what happens is it's not 0.04, it's not 23, it's neither of them. Well, it turns out what this number is actually the average between this and this. And it's all because of the Fourier convergence theorem, the fact that we chose these endpoints where it doesn't converge. The theorem tells us if we choose a value in the interval, then everything we found, the sum, the Fourier series will converge to the f(x) value. It'll converge to, like when we used, like in that other video when I chose 0, it was in the interval, so the series converges to e to the 0. But the theorem also tells us that at the endpoints, the series will converge to the midpoint of the left and right-handed continuities of the two values. So what you could do is, like clearly if we graph this, and I can do it very rough because it's going to be obvious, because the graph of e to the x is something like this, right? But for our Fourier series, it's going to be periodic, and it's only going to make sense in this region. So like for the Fourier series, from if we say this is minus pi and this is pi, it's going to match in this region. But because we did something periodic, what's going to happen is it's going to like repeat in this kind of pattern like this. So you're going to have this continuity here, like this. And so what the convergence on this tells us is that we're using these endpoints here, what we're going to get back, I know it's a poor graph, but what we're going to get back is the midpoint. So what we can do to straighten all this up is what I really want to do is I want to get the value, I've already done it another way, but let's get the value of this sum. But knowing it's the midpoint, it's pretty easy because we're saying it's the average of these two. So we're saying this sum is going to be just e pi plus e minus pi over 2. But this value is the same thing as just cosh of pi. If you put that in a calculator, you get like 11.59 or something. So we can use this to set up an equation, something like we can say that cosh of pi is going to equal all this. Well, if I just multiply the reciprocal of this thing on both sides of the equation, what we're going to have is 1/2 plus s equals pi cosh of pi over this thing. But then I can just subtract off 1/2 in order to isolate our sum. This goes away, we've isolated our sum, but I can clean this up a little bit because cosh is going to be this thing. I can take the 2 out and we can write this for the final solution. We can write this as pi over 2 hyperbolic cotangent of pi minus 1/2, and that's it. Okay, so there you go, complex Fourier series, e to the x. Thanks everyone for watching. Have a good day.